Here we go. We're back better than ever, and tonight is all about absolute extrema. And as you may predict, this is kind of a big umbrella term for a combination of absolute maximums and absolute minimums. And what we have here is, first of all, you'll notice we have a closed interval. The function starts here and it ends here. We're not going to let it tail towards either infinity in either directions. And over this interval, of all of the critical points, we're going to say that the very tallest one, the single greatest of all the maxes, is right here. And then the single greatest of all of the mins is right here. Now, a couple of differences between a relative and an absolute. First of all, absolutes can occur at both interior points, which you see here, or it could occur at an endpoint, which is the case in this particular example. By comparison, relative extrema can only occur at interior points, and you could never have a relative max or min at one of the endpoints. That would be impossible. Here's our first monster definition of the night, and it actually comes in the form of a theorem, and we name this theorem the extreme value theorem. And basically it goes like this. If f is continuous, so there's our one big requirement or prerequisite, over the closed interval from a to b, then from there we can guarantee that f has both an absolute minimum and an absolute maximum somewhere on that interval. The example I like to use here is maybe you have a phys ed class with exactly 20 students in it. 20 is a finite number, kind of similar to the fact that we've got a closed interval from A to B. And of those 20 students, maybe you decide we're going to have a chin-up contest. And within that class, now I'm not sure how many pull-ups it's going to take to win this contest, but somebody's going to win the contest. I don't know if it's going to be 3 pull-ups or 8 or 12 or 20, but somebody's going to win that contest, and that would be the winner would be our absolute max. You know, maybe someone like the great and mighty Colin Mills. And then on the flip side of that, there's probably somebody that's going to do less chin-ups than everybody else in the class, and they would be considered mathematically the absolute minimum in that case. Now, let's add another twist to that definition here. And this is the way that I've seen it on recent AP exams. And we said, well, if f's continuous on the closed interval, again, same first half of the sentence, then there is a number c, okay, within that closed interval from a to b, such that f of c is greater than or equal to f of x for all other values of x within the interval. And really what we're saying is there's a particular number c that is taller than, and that's what we're really saying there, taller or higher than every other point within that closed interval. And when we say taller, what we're really indicating is that that's the absolute max. And then we could rewrite the same sentence basically with a less than or equal sign to justify an absolute min. Now, frankly put, the extreme value theorem is an example of what we call an existence theorem. Okay? This is an entire family of theorems that prove the existence of some idea or concept. And the EVT, abbreviated for extreme value theorem, it's an existence theorem because basically it tells us or guarantees the existence of a minimum and a maximum value, but it doesn't really tell us how to find these values. It just says, you know what, hey, if f's continuous between A and B, then I guarantee that somebody's going to be the tallest and somebody's going to be the lowest point on that graph. Some other examples of existence theorems that we're going to cover in the near future are the IVT, which is an abbreviation for the intermediate value theorem, and you may have flirted with this theorem in pre-calc. And then the big granddaddy of them all is the MVT, or the mean value theorem, and this is a major concept in our course that we'll revisit throughout the year. Okay, I want to just go over briefly what's the difference between a relative extrema from the other night and an absolute extrema that we're talking about tonight. So by definition, we said that a relative extrema is any point on the curve such that f changes from increasing to decreasing. Or in other words, we said f prime was going to change from positive to negative. So for instance, I've got a relative max right here, and I've got a relative max right here. These relative extremas, though, can only occur at interior points. They cannot occur at endpoints. So for instance, this point right here cannot be considered a relative max because I'm not sure from this point, does the graph actually turn or does he continue to rise? And I'm not sure, so I can't call it a relative max. And then I've got a relative min here, I've got a relative min here. Whereas the absolutes, they could occur at any of the interior points or the endpoints. So for instance, I think this is the single lowest point on the graph, so that would be my absolute minimum value. And then this is right up here is the single tallest point on the graph, so that would be considered my absolute maximum value. You could have multiple relative maxes and multiple relative mins scattered throughout the graph, but you'll only have one absolute max within the closed interval, and you'll only have one absolute min within the closed interval. Oh, finally, it's time to get our hands on a real live example. We've thrown a lot of theoretical baloney at you so far, and I think now it's time to see if we can make any sense of it and apply it to a real live problem. And I want you to consider the function f of x equals 4 minus x squared. Just a really nice, friendly quadratic function. We've got a y-intercept at 4, uno, dos, tres, cuatro. So there's my y-intercept. And my x-intercepts are going to be at positive 2 and at negative 2. And we'll draw a quadratic that opens downward here. And let's see. And of course, all polynomials that have whole numbers for exponents are considered and guaranteed to be continuous. But I want you to consider the closed interval from -1 to 3. And within that closed interval, can we find the absolute maximum value and the absolute minimum value? And so I'm going to redraw my picture here quickly. And when x equals -1, the function's at 3, and then it goes up to 4. It's going to cross at 2, and then by the time I get to x equals 3, I'm way down here at -5, I believe. Okay? So within this restricted interval, my absolute max is right there. And today, when I say the word value, I want you to always think y-coordinate, and the absolute maximum value is 4. Now it occurs at x equals 0, and that's another difference between relatives and absolutes, is absolutes usually describe the y-coordinate. And then the lowest point is going to be right here, and I could say that the absolute minimum value is going to be -5. Okay? Now what if I used the same function, but I wanted to change the closed interval, and now I'm going from -2 to 1. And when x equals -2, the value is 0. We're going to go all the way up to 4, and then when x equals 1, we're at 3. So we're going to go up and down, and within this closed interval, my absolute max is again 4. So we got our absolute max value is 4. Okay, again, if I use the word is, I'm usually thinking y-coordinate. And in this case, the absolute minimum value is going to be 0. It occurs at -2, but the value is 0. So the absolute minimum value is 0. One more. Let's try, okay, what if I go from -2 to 2? We're going to run into a perplexing issue here. Alright, so we start here, we go up to 4, and we come back down. So, okay, piece of cake. Absolute max is at 4 again. We've got that down under control. But where's the absolute min? Well, we've actually got a tie. Okay? And in this case, well, it's a tie, but there's really only one answer because both of these points share the same y-coordinate. It just happens to be 0. So I would still say that the absolute min is 0. And so it doesn't really... Of all the y values, that's the single lowest one. No matter how many times the graph achieves a height of 0, that's my single answer. Now, unfortunately, the problems aren't going to be quite as easy as the function we had on the last example where we used 4 minus x squared, and it was so easy to draw the function. So I'm going to give you what we use is called the closed interval test for absolute extrema. So really highlight this. And so over the last couple of days, we've thrown a lot at you. We've gone over the first derivative test for relative extrema. We did the second derivative test for relative extrema. And now we've got the closed interval test for absolute extrema. And basically the closed interval test is just a fancy name for making a table of values. But here we go. I want you to first find all of the critical numbers. The critical numbers within the open interval from a to b. Now, how do you find critical numbers? Well, we're going to figure out when is f prime equal to 0 as well as when is f prime undefined. Okay. The second thing I want you to do is then evaluate f at each of those critical numbers. Now here, I want you to highlight this. Evaluate f. So after I get those critical numbers, I'm not plugging them back into f prime. I'm plugging them back into f. And that's one of the major differences between the first derivative test we did the other night when we made the sign chart and then what we're doing tonight with the closed interval test. Then the third step, I want you to evaluate f at each of the endpoints. And then from there, you're pretty much done. All we got to do now is say, well, the least of all of these values is going to be called the absolute min. And then the greatest of all of these values is going to be called the absolute max. And that's all there is to it. All right, I want you to consider the function 3x to the fourth minus 4x cubed, and our job is to find the absolute extrema, in other words, the absolute maximum value and then the absolute minimum value. And according to the closed interval test, the first thing I want to do is get my hands on the derivative. Seems to be a common theme over the last week or so. If nothing else, just take the derivative and see what happens, right? And then we're going to set this bar equal to 0, and the GCF was 12x. Factor it out, I got x minus maybe 12x squared, and then x minus 1. If I tee that bar up, we get x equals 0, x equals 1. Now, what you'll notice is that both of these critical numbers fall within the interval. If for some reason one of these critical numbers didn't fall within this interval, I would just politely disregard them and throw them out. So now, from this case, I'm going to combine steps 2 and 3 that we just listed on the closed interval test. Let's see if I and I'm going to make a gigantic table of values. And here are my x values, here are my f of x values, and I'm going to include my 2 endpoints, and then I'm going to include my 2 critical points. I'm going to plug them all into f and see who's the biggest and who's the smallest. So let's see. If I evaluated, let's see, f of negative 1, it'd be 3, negative 1 to the fourth, minus 4, negative 1 to the third, and let's see what I'm getting. I'm getting a positive 3, I'm getting a positive 4 because of a negative times a negative. I got 7 right there. And then I want to evaluate f of 0, but that's just 0. That's a nice one. F of 1 appears to be negative 1. And if I can do 2 in my head, maybe I better write this out, make sure I don't screw this up. I got 3 times 16, because that's 2 to the fourth, minus 4 times 8. And let's see, 32, 48, minus 32. How about 16 there, it looks like. All right, so what are we saying? We're basically saying, without actually physically graphing this function, that this would be the tallest point, and then this one would be the lowest or the least. So my absolute maximum value is 16, and my absolute minimum value is negative 1. Hey, you know how these usually go. We gotta finish the video tonight with a real big bear. So roll up your sleeves, put your hard hat on, and let's get to work. So closed interval test says I've got to get the derivative. So I got 2 cosine of x, and then I'm thinking I got a little miniature chain rule, and so I've got positive sine of 2x multiplied by 2 from the inner function. And I need to set this bar equal to 0 and find out all of the critical points that fall within my closed interval between 0 and 2 pi. Now check this bar out. You see this little double angle right here? So I'm going to use one of the identities from Algebra 2. And you may or may not feel comfortable with that, but let's see. So the sine of 2x is 2 sine of x cosine of x. And if you're a little shaky on your double angle formulas, you're more than welcome to grab that bar stack and look those up and check out sine of 2x and cosine of 2x. And so I've got 2 cosine of x plus 4 sine of x cos of x equal to 0. Now as far as factoring that goes, I'm going to pull out a GCF of 2 cosine of x. The first term would then become a 1, and the second term would then become 2 sine of x. Now that I've got it factored completely, I'm going to try to tee it up here. And I'm going to set 2 cosine of x equal to 0. Of course, divide both sides by 2, and that term's gone. And then I've got 1 plus 2 sine of x equal to 0. And I'm going to get sine of x is equal to negative 1/2. Now again, my closed interval is between 0 and 2 pi. For cosine, and if you want, you could draw yourself a little picture of cosine, and we're looking for pi over 2 and 3 pi over 2. Those would be the 2 times where cosine crosses the x-axis. And then for the sine function, my reference angle would be 30, but I'm looking for quadrants 3 and 4 because of the negative value. So let's see. 210 would be 7 pi over 6, and 330 would be 11 pi over 6. So, oh my garage, a lot more work than the last example, because I've got, let's see, 4 different critical points that fall within the closed interval. So by the time I consider my endpoints and my critical points, I've got 6 total values that I've got to test, and I've got to try to plug back into the original function here. So we're going to go real big table of values. X, we're plugging them all into where? Not the derivative today. We got to plug them back into f in endpoints of 0. And let's see, I'll try to go in numerical order here. We'll go pi over 2. And then let's see, 7 pi over 6 would be next. And then 3 pi over 2. And then 11 pi over 6. And then we'll finish with 2 pi. We'll squeeze him in there at the bottom. And again, we're plugging them into the original. And it fell off my screen, but it's 2 sine of x minus the cosine of 2x. And I'm going to go ahead and try to evaluate these. And I'm going to brush through these a little bit. I've got a lot of confidence that you guys can plug these all in, or you probably wouldn't be taking AP Calculus. But when I plugged in the 0, I got -1. When I plugged in pi over 2, I got 3. 7 pi over 6 was -1.5, or 3 halves. Let's see, 3 pi over 2 is -1 again. 11 pi over 6 was -3 halves again, and then -1. So pretty interesting function. My curiosity kind of got the best of me, and I was wondering, what in the world does that look like? So I'm starting at 0, -1. I got to go all the way up to 3. I come back down to -1, or I should say -1.5. So that's a little bit lower, and then back up to -1, back down. So this is a really wild function we've got here with some nice twists and turns to it. So within that group, where's your biggest number? Boom, right there. So my absolute maximum value is 3. 3, 3, 3. And what's the lowest number? Well, it's kind of a tie, but the one single number here is -3 halves. And so I would just simply say that the absolute minimum value is -1.5 or -3 halves, and those are the two answers we need. So we're going to try to keep these separate: the first derivative test, the second derivative test, and now the closed interval test. The closed interval test is the only test that I'm ever going to give you for absolute extrema, so that'll keep it a little simpler. All right, thanks for hanging in there. We'll catch you tomorrow.